Okay, so in this video, we want to begin our study of something called graph theory. This is a very important topic, uh, not only in mathematics, but also in computer science. And so let's just jump in and take a look at a definition of a graph. I will say this, graph theory is probably new to most students. It comes with a lot of terms and definitions, so we can try to speak the same language. So in this section and the subsequent ones, there's going to be a lot of new terms that it's imperative for us to understand. That way, when we say certain things like vertices or edges or loops or paths or cycles, we can all understand what it is we're talking about. So here's the definition of a graph. A graph, which I will call G, consists of a set of V of vertices and a set E of edges, such that each edge in E is associated with an unordered pair of vertices. If I have an ordered pair of vertices, then I get what is called a directed graph or a digraph. So a graph is fairly simple. It's consists of two sets, what we're going to call set V, the vertex set, and set E, the edge set. And there's going to be some relation between the vertex set and the edge set. So here's a very basic example of a graph. In this vertex set V are the vertices V1, V2, and V3. Some books will call these nodes, okay? But for this course, we're going to call them a vertex or a plural vertice. But in some texts or in a computer science context, you might call them a node. And then there's also this edge set, E, with edges E1, E2, and E3. So there are three vertices in the vertex set. There are three edges in the edge set. And so what this graph is simply saying is that I can travel from V1 to V2 via edge 1. Now, I could also then travel from V2 back to V2 via edge 2, or I could travel from V2 to V3 via edge 3. And so we have these vertices and these edges that make up this graph. Now, let's take a look at several definitions, and we won't take a look at all of these, but it is imperative that we understand the bulk of these terms and definitions. So a path is a set of edges from vertex V sub I to V sub j. So for this graph right here, I gotta have a path from V1 to V3 by taking E1, then E3. So this path might be V1, E1, V2, E3, and then V3, where I travel from vertice along an edge to another vertice, and then along a different edge to vertice 3. And so we would simply call it this a path. Adjacent edges are two edges that share a common vertex. So if I take a look, E1 and E3 are two edges that share vertex V2. So those are simply adjacent edges. Adjacent vertices are two vertices that share a common edge. What would that be? Well, V1 and V2 are adjacent vertices because they share the edge E1. A loop is an edge incident on a single vertex. In essence, an edge that connects a vertex to itself. So in this graph that we are looking at right here, E2, edge E2 is a loop because it connects vertice V2 to itself. Parallel edges are edges E1 and E2 if both are associated with the vertex pair V1, V2. Now in this graph above right here, there are no parallel edges, but if I wanted to draw a quick graph, I could have V1, V2, and let's say I could get to V1 to V2 via edge E1, or another way, via edge E2. In this instance, E1 and E2 would be said to be parallel edges. An isolated vertex is a vertex that is not incident on any edge. What would this look like? If I looked at this same graph right here, and then let's say I threw another vertex out here by his lonesome self, and I called him V4. But notice there's no edge V4 to connect him to any other vertice or even to himself. So in this instance, this would be called an isolated vertex. Now, the degree of a vertex is a very important definition. The degree of a vertex, notated DEG parentheses V, is the number of edges incident on V. Note, the degree of a loop is 2. So if I take a look at this graph that's above me right here, the degree of V1 is simply 1. Why is that? There is one edge that is incident on V1. Well, what about V3? The degree of V3 is also 1. Why? There is one edge, namely E3, that is incident on V3. Now, what about the degree of vertex 2? Well, let's count. Vertex 2, I have edge E1, I have edge E3, and then I have this loop E2, and the degree of a loop is 2, so I have 1, 1, and 2 for a total of 4. So the degree of vertex 2 is 4, and I can count it really easily. 1, 2, 3, and 4. There they are right there. Okay, a couple more terms. The order of a graph is the number of vertices in the vertex set. So in this example, the order of this graph would be 3. There are 3 vertices in the vertex set. The size of a graph is the number of edges in the edge set. So the size of this is also 3. There are 3 edges in the edge set. Now, we say a graph is simple if the graph has no loops nor parallel edges. Now, it should be evident to the student that this graph that we are introducing right here is not a simple graph because of this loop E2, okay? If I were to remove this edge E2, then yes, I would have a simple graph. So, lots of terms and definitions. Let's pivot and take a look at some common graphs. The first is the null graph n sub n. So n sub 1 is simply a vertex V1 but no edges. N sub 2, the null graph on 2 vertices. So this would be V1 and V2. Notice no edges. N3 would be the graph on 3 vertices, V1, V2, V3. Notice for all of these null graphs, though, it consists strictly of a vertex set, but no edge set. In essence, the edge set is 0, or the empty set. There are no edges in these graphs. Now, let's take a look at what we would call the path graph for n greater than or equal to 2. So what would P2 look like? P2 would be a path from V1 to V2. And if I wish to label this edge, I could call it E1. P3, the path graph on 3 vertices. Well, you guessed it, V1, V2, V3. There's a path from V1 to V3. If I wish to label edges, I can. E1 and E2. We'll do it one more. P4. You can see the pattern. V1, V2, V3, V4, etc. So we call these the path graphs. Okay, the cycle graph for n greater than or equal to 3. Okay, so let's take a look at what I'm going to call C3. The cycle graph on 3 vertices would be V1, V2, V3. Notice you can see why we would call this a cycle. We haven't defined what a cycle is yet, but you can see how I could travel from V1 to V2 to V3 and then back to V1 and make what we're going to call a cycle. C4, the cycle graph on 4 vertices, would be as follows: V1, V2, V3, V4. C5, the cycle graph on 5 vertices. Like so. And I can extend this for however many vertices I wish for all of these guys. Okay, let's continue to take a look at common graphs. The complete graph, G equaling K sub n, is the simple graph. Okay, what do I mean by simple graph? That means no loops. When I say simple graph, that means no loops or parallel edges, in which there is an edge between every pair of distinct vertices. Okay, so let's take a look. K2 would be this graph, V1, V2. Notice this is the same thing as the path graph on 2 vertices. K3, V1, V2, V3. This is the same as C3, the cycle graph on 3 vertices. And now, as we progress, you're going to see why this is called the complete graph. If I do K4, K4 would look like this. In essence, let me explain it as I draw it. I'll start with the vertex set. I have 4 vertices, V1, V2, V3, V4. And to make this the complete graph, there's an edge between every pair of distinct vertices. So in essence, I can get from V1 to V2, I can get from V1 to V3, I can get from V1 to V4. I can get from V2 to V1. Remember, this is a simple graph, so no loops, no parallel edges. So I'm not going to draw any loops. I'm not going to draw any parallel edges. So currently in this graph that's drawn, I can get from V2 to V1, but I also need to be able to get from V2 to V3 and from V2 to V4. And then lastly, I need to be able to get from V3 to V4. And so, as you can see, in this complete graph, what it's saying is I can start at any vertice, and then I only have to travel across one edge to get to any other vertice. And so we call this the complete graph on 4 vertices. Let's do one more. K5. So K5 would look like this. So 1, 2, 3, 4, 5. Vertices V1, V2, V3, V4, V5. And I need to draw this in such a way that I can get from any vertex to any other vertex along a singular edge. So I can get from V1 to V2 to V3 to V4 to V5. I need to be able to get from V2 to V3 to V4 to V5. I need to be able to get from V3 to V4 or V5. And I also need to be able to get from V4 to V5. And so this is the graph, the complete graph, on 5 vertices, simply meaning pick any vertex and there is an edge that will connect that vertex to any other vertex. But notice there are no loops, there are no parallel edges. Okay? The way that this K5 looks like, if you take a look, I have this star inside this pentagon. And so we would call this K5. Okay, let's slide to the next page and discuss what is called the complete bipartite graph. The complete bipartite graph, K sub mn, is the simple graph. So when I say simple graph, that simply means no loops, no parallel edges, whose vertex set is partitioned into sets U with m vertices and V with n vertices, in which the edge set consists of all edges of the form U1, V1, with U1 coming from U and V1 coming from V. Okay, I know that seems like a lot. We'll take a look at a couple of examples. So K 2, 3. K2, 3. So in this set, the set U would be U1, U2. There are 2 vertices in this vertex set. V would be V1, V2, V3. There are 3 vertices in this set. Okay? Now, notice that U intersect V is the empty set. And U union V is the set U1, U2, V1, V2, V3. Now, let's draw this graph. I'm going to have 2 vertices in this first set. I will call them U1 and U2. And then 3 vertices in this second set, which I would call V1, V2, and V3. Now, Because this is the complete bipartite graph, this means that U1 has an edge to V1, V2, and V3. Similarly, U2 has an edge to V1, V2, and V3. Notice, there is no way to get from U1 to U2 directly. I would have to first travel to a vertex in the V set and then travel back to my vertex in the U set. So in essence, I can't get from U1 to U2 without first visiting a vertex in the V set. The same is true for vertices over here. In the V set, I can't get from V1 to V2 unless I travel to one of the U's in the U set, like so. And so we would call this K sub 2, 3. But I could easily change up my values right here. Instead of K sub 2, 3, what if I had K sub 3, 3? Well, in this instance, I would have 3 vertices in the U set, U1, U2, U3, and 3 vertices in the V set, V1, V2, V3, and I can only travel from one vertex set across to the others. So I can get from U1 to any V, I can get from U2 to any V, or I could get from U3 to any V. And so we would call this graph K 3, 3, the complete bipartite graph with 3 vertices in the first set and 3 vertices in the second set. Now, this brings us to a very important summary chart that summarizes the orders and the sizes of common graphs. If I have the null graph n sub n, the order, which is the number of vertices, is simply n. But if you recall what the null graph looked like, there were no edges in any of them, so the size of the edge set would be 0. The path graph on n vertices has n vertices and n minus 1 edges. The cycle graph on n vertices has n vertices and n edges. The complete graph on n vertices has n vertices and n times n minus 1 over 2 edges. This refers back to the handshaking theorem from a previous section. The complete graph, the complete bipartite graph with m comma n vertices, it has m vertices in the first set, n in the second set, for a total of m plus n vertices and m times n edges. Okay, let's slide a couple of slides down to this definition right here. So let's say that I have U and V, and they are vertices in a graph G. And edge E is a bridge if G take away E has more components than G. A simple path from U to V is a path from U to V with no repeated vertices. If I do not repeat the vertices, then I say it is a simple path. A trail from U to V is a path from U to V with no repeated edges. So if I don't repeat edges, I call it a trail. Okay, a cycle or a circuit or a closed trail is a path of non-zero length from V to V with no repeated edges. I will primarily use the term cycle, but all of these are synonymous and different texts will call them different things. But a cycle, I start at V, I get back to V, but I don't repeat any edges. So let's take a look at an example. Okay. Let's say I have a graph that looks like this. And I'll just label these V1, V2, V3, V4, V5, V6. And I'll switch colors for the edge set. So we'll call this E1, E2, E3. We'll call this E4, E5, E6. And we'll call this E7, E8, and this edge right here, E9. Okay, so let's do this. We'll just do a couple of these. Okay? Let us find a simple path from V1 to V5. Now, I'm not saying that this path is unique by any stretch, okay? I'm simply stating that we can hopefully find a simple path from V1 to V5. Okay, so I need to go from V1 to V5 with no repeated vertices. So V1 to V5 with no repeated vertices. So let's see here. I could go V1, E4 to V4, take E8 to V5. And so that is one path. But the astute student can see that there are multiple paths. I could go V1, E1 to V2 to E5 to V5. And notice that was a different path. This first path traveled like so. This second path like so. Okay. Let us find a cycle from V1 of length 4. Okay, so all this is saying is I wish to start at V1. I wish to end at V1. And I want the length of this cycle to have 4 edges. So let's take a look. I could go, and this is by no means unique, I could go V1, E1, V2, E2, V3, E3, back to V1. That is this route right here. In essence, I am traversing this outer triangle like so. Now, that's not the only cycle. I'll do a different one. Start at V1, end at V1. Okay. What if I went like so? Here to here to here to here. Well, what is that cycle? So that's V1, E4, V4, E7, V6, E6, V3, running out of space, E3 to back to V1. So 1, 2, 3, 4, like follows. Okay, so let us now slide down here and briefly discuss isomorphic graphs. Graphs G1 and G2 are isomorphic if there is a bijective function, meaning, if we recall from our section on functions, a one-to-one and onto function, f, from the vertices of G1 to the vertices of G2, and a bijective function g from the edges of G1 to the edges of G2, so that an edge E incident on V1, V2, and G1, if and only if the edge G of E is incident on F of V1 and F of V2, excuse me, there's a typo right here, in G2. The pair of functions f and g is called an isomorphism of G1 onto G2. The word isomorphism means same form. So let's take a look at a couple of pictures right here. This first graph right here, this star-looking graph, okay? Notice that there are 5 vertices in this vertex set and a total of 1, 2, 3, 4, 5 edges in this edge set right here. And notice that each vertex is connected to only 2 other vertices. Now my claim is that this graph, I guess you'd call it a star graph right here, is isomorphic. This is the symbol that we sometimes use. Isomorphic, same form, as this graph right here on the right. Well, what is this graph here on the right? This is C5. This is the cycle graph on 5 vertices. And so these 2 graphs, excuse me, have the same form. If I take a look at one other one, okay. So this graph here on the left, if I look carefully, and compare it to this one here on the right. Notice this is a rectangle inside of a rectangle. Okay? These two graphs are of the same form, and so I would say that graph A is isomorphic to graph B. Now, these are saying the same thing. One of them, in my opinion, looks much cleaner or easier to read than the other. I think it's easier to take a look at graph B, perhaps. So that will conclude our lesson on graph theory introduction.